Okay, so now to section 3.3 in algebra. And now we're going to look particularly at linear functions. So when we're graphing functions and they form a line, they're called linear functions. And when we give a table of linear functions, there's actually a pattern to the table. We can look at how the x values change and how the y values change to get an idea of how to write an equation that will represent that table. And so when we're looking at this, we have something called our rate of change. And so this is kind of the rate of change. And so it's looking at how my y values change and how that corresponds to how my x values change. And I'm going to use that to help figure out what number goes in front of x in my equation. Now, the last value is actually what we call a starting value. It's the output, or it's our y value, when x is equal to 0. So when x is 0 in the table, I'm looking for what is that y value. And that's the number that's going to go right here. So we're going to look at a couple problems. So our first problem, we've got this table, and what I'm going to do is I'm going to look at how do my x values change. So here my x values are changing by each time I add 1. Now I'm going to look at how my y values change. So my y values each time I am adding 1. So when it comes to my equation, I'm going to write y equals, and then up here it tells me I'm going to put the y on top and the x on bottom. So y on top, x on bottom, and that's going to give me that value. So 1 over 1 times x. Then I have to look back at my graph, and I want to know where my starting value is. So I'm looking at where x is 0. And where x is 0, I have a y value of 9, and that's going to go right here. And so now I'm just going to write this nicer. So this simplifies. 1 over 1 is really 1. So my equation is y equals 1x plus 9. And that's it. So we'll look at the next problem. And we're going to go ahead and look at how our x values change. So each time, let's see, a little hard to tell with negative numbers, so sometimes I'm just looking at positive. So 0 to 3, I'm adding 3, 3 to 6, I'm adding 3. So each time I'm adding 3, so that's my change in x. And then I'm going to go ahead and look at the y's. So change in y. So 5 to 7, 7 to 9. So it looks like each time I'm adding 2. So now what I'm going to go ahead and do is I'm going to work on writing that equation. So y equals, and I put the y on top. So the y changes by adding 2. The x changes by adding 3. And then I put my x. Now I have to find that starting point. So I'm going to go to my table. When x is 0, y is 11. So this should be plus 11. And that's our equation. Okay, so now we're going to go ahead and look at special examples. So again, we're going to write the equation for these. But now we have something a little weird, because now we've got a really tiny table. I can still look at how my x changes. How does x change? Each time I add 1. Can look at how my y changes. Each time I'm adding 2. So now my equation is going to be y equals, and then I put the y on top, how y changes, over how x changes. But now I don't have a 0. So when I'm looking for the 0, all of a sudden there is no 0. So I'm going to go ahead and put a 0 right here. And I'm going to work backwards. So this way I'm minusing 1. So this way I'm going to go backwards, and instead of adding 2, I'm going to minus 2. So what is 1 minus 2? So I'm taking this value and I'm minusing 2. and I get a value of -1. So that means this is -1. So if it helps you, you can even just build a new table. You can start at 0 and go 1, 2, 3, and then you can say, okay, well, this is 1, 3, 5, but if I work backwards, 5, 3, 2, 5, 3, 1, and then I go down 2 more, gives me -1. So you can use that idea of working backwards. -2, -2, -2. Okay, so we have another one. It's not put in a table. But we've talked about how to take this and put it into a table before. So we're going to go ahead and we're going to start. And there is no 0, so I'm going to leave myself a spot for 0. And I have 5 and 4, 10 and 7, 15 and 10. So now we're going to go ahead and look at that pattern. What's happening with my x's? So it looks like I'm adding 5. Then I'm going to look at what happens with my y's. It looks like I am adding 3. But now I want to work backwards so I can get this. So -3, -3, 4 minus 3 gives me 1. And now I can write that equation. So my equation should look like y equals, I put the change in y over the change in x times x, and then I use that starting value. And there's my equation. So we'll be practicing this. We're going to hit it again real hard in lesson 6. So we'll keep seeing it. We'll have lots of time practicing. But the more you practice it, the better you get at this. Okay, the next thing we're talking about is our whole input and output. So the input of a function is known as our independent variable. Our output of a function is known as our dependent variable. So when I'm talking about input, I'm talking about our x value. When I'm talking about output, I'm talking about our y variable. So our input or independent variable is going to be x. Our output or dependent variable is y. And the reason why y is the dependent variable is because we always calculate y based on what x is. X tells me what y is going to be. So kind of like when you're working, how much you get paid depends on the number of hours you work. So the hours you work is your independent variable. The amount you get paid is your dependent variable because the pay depends on the number of hours worked. And so that's kind of how we're looking at this. So when I'm looking here at my sample problem, a painter must measure room before deciding how much paint to buy. So what's independent? What do we have to figure out first? Well, measure of the room. Now our dependent variable is what we're using that to figure out. So our dependent is amount of paint to buy. Okay, the height of a candle decreases d-centimeters for every hour it burns. So our height is dependent on the number of hours that the candle is burning. So our independent variable is hours burned. And based on that, we can figure out our dependent variable, the height of the candle. Okay, a veterinarian must weigh an animal before determining the amount of medication. So we need to first know the weight of the animal, and then we can decide the amount of medicine. So independent is what we have to know first. And dependent is what we're using that to figure out. And that is amount of medicine. Okay. If a relation is a function, we can rewrite the equation for the relation in what we call function notation. And so this is a really, really big one. Function notation replaces the letter y. So instead of y equals something, we write f parentheses x. And when we see that f parentheses x, it's not f times x. It's read f at x, which is saying the value of my function at this x value. And so it allows us to shortcut writing out a bunch of words to help you understand what's happening. So for example, we have this function y equals 3x plus 5. When I write it in function notation, it now becomes f at x equals 3x plus 5. And so you can notice how this y is just being replaced with this f at x. Now, if I want to know what happens when I replace x with -2, oops, not what I wanted to do. I wanted to highlight. So when x is -2, we write find f at -2. So the -2 replaces x in that notation, which tells you replace x with -2 in your equation. And so that's exactly what we do. We take that -2 and put it in the x spot, and then we simplify this side. I'm simplifying that side. This -2 over here, I don't do anything with it. It's just hanging out there chilling, just saying that when x is -2, this is my answer for y. So we're going to try some sample problems. Our first one is f at x equals 2x squared minus 9. So if I want to find f at 3, I'm going to plug in 3 wherever there's an x. So this is going to be 2, and at the x point, I'm going to put 3. And then I'm going to simplify that. So the first thing I do in order of operations is my exponents. So this is going to be 2 times, well, 3 times 3 is 9. So 3 squared is 9. Then I multiply, so 2 times 9 is 18. And then 18 minus 9 is 9. And that's it. That's our value of our function at 3. So on our next one, I'm now going to plug in -3. So my function at -3 equals 2, and then in that x spot, and remember I'm getting that function from right up here, 2 times -3 squared minus 9. So again, like our last problem, we do our exponents first. That's order of operations. So -3 times -3 is positive 9. And then 2 times 9 is 18. And then 18 minus 9 gives me 9. So the value of my function at -3 is 9. And that's it. That's all I'm really doing. Okay, so for my next one, now I have a new equation with a fraction. So now if I want to find f at 6, I'm going to put 6 wherever there's an x. So now I have 2/3 x, so I put in 6, plus 5. Now when I'm multiplying this fraction times this number, I can turn 6 into a fraction by putting it over 1. And then I times the top and I times the bottom. So f at 6 equals 2 times 6 is 12, 3 times 1 is 1. And now I divide. So 12 divided by 3 becomes 4. And 4 plus 5 gives me 9. So the value of my function at 6 is 9. And for our last one, we're doing the same thing. Now we're going to plug in -3. So the value of my function at -3 is 2/3 times -3 plus 5. And again, I could put that function over 1. I times the top. I times the bottom, so I get -6 over 3. And then I divide. The negative 6 divided by 3 gives me negative 2. So negative 2 plus 5 is 3. So the value of my function at negative 3 is equal to 3. And that's our function notation. Just a fancy way of writing things so we don't have to use as many words. Because in math you'll find that we do so much as it is, we don't have to write out a bunch of words and write an essay on how it works anyway. Okay, so going back to independent and dependent variables and writing an equation of the function in function notation. Okay, so a fitness center charges a $100 initiation fee plus $40 per month. So what I have is how many months and then how much we're charging. So the amount we charge is based on months. So my independent variable is months. And my dependent variable is money charged. Now I can use any letters I want, but I like sticking with x. So when I write my function, I'm going to write my function of x equals. So there's my function notation. And now I want to talk about what is our initial fee. We have a $100 initial initiation fee. And then I'm going to add on $40 for every month that we're a member. So again, it's using that standard way of writing an equation that we've been working on. Our initial fee plus our rate, how much we charge every single month, or how much we charge an hour, or how much we charge a day. And that's our function notation. Okay, amusement park charges $6 parking fee plus $29.99 per person. So it looks like we're using the amount of people to determine how much money the amusement park is charging. So our independent variable is people, or number of people, and our dependent variable is money charged. So when we write our function, we're going to write f at x is equal to, and our initial fee is that $6 parking fee. And then we're going to add on $29.99 for every person. And that's it. Okay, so when we start looking at domain and range of a function in a real world situation, we're going to find that every real number is not reasonable when we start talking about domain and range. Because, especially if you look at our last situation, are we going to have negative people going to the amusement park? No. So when we're looking at this, negatives are not always something you can use for a real world situation. So even though it may work mathematically on its own, when you think of the context, when you think of the situation, it doesn't always work. So you have to be careful about those negatives, and you also have to be careful of those discrete graphs. Like, you can't really have half a person. Even if a person's missing their legs, they're still a person. Don't degrade them by saying they're not a person. So those are something that when you think about this domain and range stuff, that you need to think about the situation. So like whole numbers can only represent a number of people. So write a function to describe the situation, find a reasonable domain and range for the function. A person can pay to have a birthday party at the theater. The cost is a $100 deposit plus $2 per person. So when I write my function at x is equal to, I've got the $100 initial fee, and then they charge $2 a person. And so now when we're thinking about this for our domain, can our domain be a fraction? Can I have half a person? Well, we just talked about this. We can't have half a person. So can my domain be negative? Can I have negative people where eventually the people are going to owe me money at the theater? I mean, The theater is going to owe people money for not having people go. It doesn't work like that. We can't have negative numbers and we can't have fractions. So these are, our domain would be whole numbers. So whole numbers are our positive whole numbers, not negatives, not fractions, not decimals. And then our range is also going to be whole numbers, but they're all going to be whole numbers greater than 100. Since the lowest I can go for X is 0 people attending this party, when I plug in 0, there's still that $100 fee for arranging a party or reserving a party. So my range is going to be whole numbers greater than 100. Or equal to, because it can be equal to. Doesn't really make sense, because why would you pay $100? And well, I guess if you cancel, then they keep that $100. So now we're put in this situation where we've talked about so many different things with our X's and Y's. So now we have kind of a little table to help shortcut us. Our independent variable is our X values, which are also known as our domain, which is also known as input, which is also known just as X. And then we have our dependent variable, which is our Y values, our range, our output, or our function at X. And so just lots of different ways to say the same thing. And if you don't understand the vocabulary when it comes to standardized tests, SAT, ACT, the AMP test, or a test in this class, if you don't understand the language, then you can't answer the question just because of a vocabulary term. And it seems silly to not be able to answer a question because you didn't understand the vocabulary. So taking time to really learn those words will be helpful on any sort of test that you have in this class or a standardized test anywhere.